Okay, please work. Okay, I think it's
Dude,
working.
I love the, who was it that who had a stroke and then his wife just ran the country? Oh yeah, what's his name? It was
U.S. president?
yeah, it'll come. Well, I mean, Alabama was pretty amazing, but no.
So for number 8, there's actually a very fascinating result on this. First of all, 8 is just a generalization of what like form, what graph. Parabola. Hopefully that's fairly obvious. It's C is the y-intercept of that parabola, and A is some constant which would effectively determine the steepness of the curve, right? So just before we get into this, does anyone think they have a thought on, I don't want to give it away necessarily, but one of these letters is not going to be relevant in the calculation of average rate of change. Which letter is it? C. Because you can shift this thing up or down. This is a big calculus idea of you can shift this function up or down, and that's not going to really affect the steepness of the curve. So,
Wilson.
Woodrow Wilson was the answer
No.
to what you're talking about?
Yeah. Not Woodrow Wilson.
Not Woodrow Wilson? Which Wilson?
No, the other one. Oh.
The volleyball from Castaway?
Yeah, the volleyball from Castaway.
Okay.
Wilson.
Wilson! That's a pretty good movie.
Oh yeah. It is Woodrow Wilson.
Okay, so if we're going from P to Q, thanks for.
I don't know. I only remember Edith Wilson. I don't really care about the others.
Okay, let's calculate the average rate of change from P to Q, right? Okay, so you gotta get rise over run. Okay, so the rise would be, like, what's this y value here? Q squared. So it'd be Q squared minus, what's that y value? P squared. Okay, so the top, so the rise is Q squared minus P squared. And what's the run? The run is Q minus P. Okay, so then if I say the average rate of change is rise over run. Oh, I messed up actually. I did technically mess up. If I want to be, actually I don't have to raise anything. Technically this y value is AQ squared plus C. Sorry about that, guys. This y value here is A times P squared plus C.
Yeah.
So my bad. I just got ahead of myself there. And also made a mistake of forgetting the A. 2 mistakes in one. So actually, this minus this, do you see the C's cancel out now though if I subtract them? So if I subtract these guys, I get A Q squared minus A P squared. Does that make better sense? Okay, so now the average rate of change. So the rise over run is A Q squared minus A P squared over P minus Q. So already we've seen the C drops out immediately. He's already gone. Now let's get fancy. This is an answer, but the point of this question is to see how simple of an answer can we get to a question like this. So can I factor out the A? Yeah. So factor out the A. Now you might already see another thing. Once the A is factored out, now it's like, oh, wait a second. We just did a problem like this yesterday where there was a difference of squares on top, right? Does that ring a bell or no?
Yes.
So P squared minus Q squared can be written as P plus Q times P minus Q. Everyone okay with that?
Mm-hmm.
And so I have on top, I have a thing times a P minus Q. On bottom, I have a P minus Q, so those cancel out. And we get this amazing answer. Just A times the sum of P and Q. Now, this is a really interesting answer to me for a few reasons. One is it kind of summarizes nicely the idea that the farther over to the right you go on a parabola, the steeper it gets. You see how the P plus Q tells you that? Because let's say P and Q are big numbers, right? If P and Q are kind of large numbers, then this average rate of change ends up being a big number, what if P and Q are opposite numbers? They cancel out. Does that agree with the symmetry of a parabola?
Yeah.
Like if P and Q are, say, -2 and +2, you get an average rate of change of 0. Right? Cool beans? Okay. All right. Also, last thing would be, let's say P was negative and Q was positive, but P was a bigger number. So you get a parabola, and let's, say your P value is -5 and your Q value is +4. What kind of average rate of change do you get? You get negative, which is again what happens here. And then lastly, you get this thing of how A just linearly affects the average rate of change. So for example, doubling the A value in a parabola formula, doubling that number would double the average rate of change over some given interval, which is a nice, very nice result. Okay, let's look at these. So hopefully you gave them a shot. A parabola, we talked about this yesterday, a parabola would turn into, so this is F, and F prime would be, you had to sort of take my word for it, that it ends up being linear. Maybe it might surprise you. But that last result actually might have given you some insight into if the average rate of change is increasing in a linear fashion, right, as you move across the function, then it stands to reason that the derivative might also do that. So anyway, there's your first result. But the main key was negative derivatives, 0 derivatives, positive derivatives translates to negative y values, 0 y value, positive y values. Is everyone okay with that connection? Of how the slopes become the y values? Más o menos? Okay. So I'll give you just a quick clarification point. So let's say that say I identified a point here. Say this was at 3. Suppose for a moment that the slope here, the slope of the tangent line was 6. That actually is true mathematically. Suppose it's true. What that means, if the slope on this graph, when x is 3, is 6, that means that this graph contains what point? 3, 6. That's what a derivative graph is doing. It's telling you about how slopey is the. Let's keep going. Now you got x cubed. Okay. So here's f. So did anyone get an answer for this that they would be willing to share with us? Yes? No.
An absolute value. B.
Very close, yeah. It turns out, so think about, that's a great answer. It's an outstanding answer because it captures everything that right now that we have the background to figure out. So, okay, look at these slopes, right? These slopes, you can kind of see how it's 0 here, right? Does that make sense? It kind of goes from, it really flattens out here. And then you can see these slopes. You get positive slopes, even more positive. You can see the slopes are increasing. But it turns out, so if you drew a flat line, it's reasonable. But it actually turns out that for a cubic, it is curved. Yeah, it actually is a parabola. Yeah, it turns out that the cubic's derivative is a parabola. And then over here, the key here is notice what's always true about these derivatives. Even on the left side, they're still positive slopes. So the left side of this graph has to also be positive. And because of the symmetry of this graph, right, the slopes have to be symmetrical. So therefore, this graph has to have symmetrical y values. Okay, so it turns out, so perhaps surprisingly, that the derivative of this cubic is actually some kind of parabola. Now, it's not x squared. I'll tell you that right now. It's not just x squared. Wow, very clever. How do you know that? Michael told you. Michael J. Knudsen. Yes, it turns out that it's 3x squared. Okay, here's 1 over x. All right. Here's the 1 over x function, so here's f. All right. This one's a little bit weird. Look at any point you can look at on this graph, what seems to be the case?
The slope is.
That's I really butchered that
It's
one.
negative.
The slopes are always negative. There's no place in this graph that has a positive slope. That's interesting. Which means all of the y values on the derivative graph are going to have to be what? Negative. So they're all going to live down here. Every single point's going to live down here. What?
I was thinking just like it would be like a negative shape graph.
Not a parabola. Let's look at what happens on the far left over here. What kind of slopes are these?
Really small.
Really small negative slopes. So I'm going to have really small negative y values.
You go get an upside down bird.
I was gonna say it's
That already did.
an upside down 1 over x squared.
Yeah, so what happens as I approach 0 from the left? Look at these slopes.
Big boys.
Those are huge negative slopes. And it doesn't seem like I actually can draw any kind of tangent line at 0. So there's not going to be a derivative at 0. So this graph does this.
Yeah.
And then by the same kind of reasoning, it does this. And this one, it turns out semi-miraculously that if you had to guess what function this is, you'd be correct. The exact, because earlier you might have said, is that x squared? And it turns out it's 3x squared.
Negative 1 over x squared.
Negative 1 over x squared. It actually turns out would be the exact. Now we're getting a little ahead of ourselves. We're not going to actually get into all the rules of derivatives until we pin down like the definition. But anyway, the last one here. But if you were curious, this would actually be negative 1 over x squared. I didn't do a very good drawing. It's this guy. It's the 1 over x squared flipped upside down. And then my favorite graph. Well, maybe not. Hard to have one favorite. You know?
Yeah, that's
So many good ones out
there
there.
are so many good ones.
It's like when someone says, "What's your favorite song?" Oh, does anyone here have a favorite song? Like, I have one song that's like definitely my favorite song. I'm just curious. The Changes. What's that for? Who's that?
No.
Like,
Oh, it right.
Like,
Changes.
changes we
Anyway,
yeah.
so
Yeah.
this is just Humpty Dumpty. So nice. Such a nice function. Let's look at derivatives though. What kind of derivatives do you have over here?
Very
Small. So you can actually build these graphs up bit by bit if you want to just go point by point. I got small positive. Okay, small positive. Put a little dot at small positive. And then they seem to get a little bigger. So they seem to be increasing. But then what happens as you start getting close to 0?
It gets small again.
Zero.
Okay, so I have to go small, increase, and then come down and hit 0. And then I have to follow the opposite mirror pattern for corresponding negative slopes over here. So, ooh, so it's got to look something like that.
Oh, I just failed. That was a terrible graph.
So Humpty Dumpty has that weird, although there's a lot of interesting connections here between even and odd functions. You may have noticed that. Even or odd function? Even.
Odd. Schneeben. 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 Schneid.
Thanky Winky. Thanky Winky. Ooh.
Yes. Wow.
What? What's confusing about it? No, things are just scary, Dylan. Okay. So I have to now go over the limit definition of the derivative. Okay. So
Oh man, I need a nap. Or maybe just a long slumber.
I'm gonna make this as painless as I can, but it's something it's absolutely essential to understanding calculus. But in terms of like applying calculus in practice, it's something that will very quickly develop some quicker rules for finding derivatives algebraically. But this definition is like, it's sort of the cornerstone of everything that calculus is about. So if any of you guys become math majors, you'll take classes that are like really are all about these like very rigorous technical definitions. So anyway, let's get into it here. I made a little thing for you here on Desmos. Okay, so I made
That's not little.
what?
That's not little.
It's a lot.
Oh, it's okay. It's just a graph. Just a graphie. He's not scary. I made a graphie. Okay, look at him. What's something you noticed about him? About his slops? They're always positive. If you're curious what the function was, I just arbitrarily chose 1 over the square root of 4 minus x. I chose that because it gets steep fast. Oh, sorry, I almost forgot Griffin. Sorry, bro. There you go. Anyway, I put a link to this on Classroom if you want to mess around with it, if anyone's curious. So anyway, I got this graph on there, just you can change f of x if you want, you make a different function. So let's suppose that I wanted this 3 here. Let's suppose I was curious about what's the slope of this function at x equals 3, like right here at 3. So the point 3, 1 lives in the graph, and suppose I wanted to know what's the derivative there. So there's the point at 3, 1. And so what I might do is say, let's look at the average rate of change between 3. Did I mess up something? So there's 3. So the technique that I would want to look at, sorry, Griffin, I don't know if you can see this at all. There's like, the camera has trouble picking up. Oh, now it's fine. Okay. Anyway, sorry, guys. Okay. So say I want to know, what is the slope right there? Okay, well, yeah, I can, of course, eyeball a tangent line. Sure. But that's not like a precise or rigorous thing, right? So what I would do is pick some other point over here and then slide that point very close to my original point. And so I do that. By the way, this hopefully reminds you of something we've studied. Starts with an L. A limit. I'm taking a limit. I'm taking this idea of what if I take this fraction, this rise over run, and I take a limit as these 2 points converge very, very, very close to each other. That's what a derivative is. It is a limit. That's why it's called the limit definition of the derivative. So one more time. So I chose an offset of 0.9. So right now this point is 0.9 to the right of this point. And then I just take the limit as that offset approaches 0. That make sense? Maybe, sort of, generally? No? Okay. Good feedback. Now, limits have to go both ways. Limits have to work from both sides. So it's actually another one I put in. So another point. And I can look at both. So now I'm looking at 2 average rates of change at the same time. This part's maybe less essential, but I have to make sure also that as h approaches 0, as this offset approaches 0, they have to be converging to the same slope. Okay? I'm going to show this to you again in a minute after we go over the definition, and hopefully it'll click for you then. Are you leaving, Aaron?
I'll watch the rest of them.
Okay, sounds good. So here's the definition. Now here I'm going to show you this information the old-fashioned way. How it was shown to me before the dawn of the computer age. Okay, you have a function. Okay.
Yeah, you give, yeah.
Okay, so here's some, oh, thank you, Jason, you're the best. Let me move it over here. It's all for you, Chris. Okay, so suppose this is some function y equals f of x. And suppose I'm interested in finding the derivative of this function. So what I do is I say, well, I'm going to pick some x value. And great, here's if this function is y equals f of x, what's the y value here? F of x, right? If you plug in x, the y value is f of x. Now what I'm going to do is apply a little offset to this. I'm going to bump this x up by a small amount. And I'm going to call it h. So if I bump up my x value by some small amount h, what's my new x value? X plus h, great. And so that's going to have a corresponding y value of f of what?
F plus h.
Very good, f of x plus h. Okay, so then I say, what's the average rate of change of this? Let's do rise over run. Rise, run. So let's use some blue here. What's the rise gonna be? Very good. It's f of x plus h minus f of x. Difference. What's the run? Just h. So therefore, the average rate of change is this fraction of f of x plus h minus f of x all over h. But I don't want the average rate of change. I want the tangent line at this point. I want to find this slope here. So I need to push this point down towards this point as close as I can. So what I'm going to do is take the limit. Take a guess. The limit as what approaches what?
Just x plus h.
X plus h.
Approaches
x. For f of x.
Those make sense. It's just going to be as h approaches 0, though. So as this bump amount, this red amount, shrinks to 0. So take the limit as h approaches 0, and this limit here would tell me the derivative of my function at that x value. So that this is the famous limit definition of the derivative. So I'll show it to you here. So here it is again on the computer. This is what taking that limit looks like. I'm starting off with kind of a big h value. Right now my h value is 0.9. So I'm starting off at 3.9. That's a pretty big h value. That's what I do is I shrink that h value down until it's really close to 0. Now truly in a limit, 0.01 is not even that close. A true limit is, we're talking infinitesimally close, but this is close enough for government work, as Michael J. Knudsen would say. So there you go. That's the process. Is this h value, average rate of change, pretty poor estimate. As we get closer and closer, you get a better and better estimate. And then if you truly take the limit as you go to 0, you get the answer. Now, can h actually be 0? No, because then you'd be dividing by 0 itself. Of course.
Yeah.
Okay, so how do you use this in practice? This is the so this first question here. Use the limit definition of the derivative to find f prime of x. Now this is kind of a silly question if you think about it, but it's necessary to show how this limit is used. Okay, so the function is, I shouldn't even say that because it's way funnier to actually use the definition, and then you get this obvious answer, and you go, oh wait, yeah, wait a second, it's obvious. Here's my function. Let's use the limit definition of the derivative. So the limit definition of the derivative says that f prime of x is f of x plus h minus f of x over h. Okay, so what's f of x plus h for this function? So this is always the thing. Okay, let's review real quick. F of x is 3 times x. What's f of 7? 3 times 7. What's f of banana? 3 times banana. What's f of banana plus hippo? 3 times banana plus hippo. Okay, so what's f of x plus h? 3 times x plus h. So when you're using this definition in practice, all you do is, for this term here, you just replace the x in your formula with an x plus h in parentheses. That's all you got to do. Then you subtract, what's f of x? Well, f of x is 3x. And you divide by h. I messed up. I forgot to say the limit. Forgive me. Forgive me. Just testing you. You don't put that. It's
Bogus.
you are rough shape. Yeah, bogus, exactly. It is bogus if you don't have the limit. Okay, so sorry about that. I forgot to write the limit. Okay, almost done. Now the name of the game on these is always to look for some kind of cancely-wancely action. Okay? It's the spice of life. I bring here. Do you see on top any cancely-wancely potential? Yeah, you're gonna have 3x plus 3h minus 3x. Wait a second, those just cancel out to 0, and then you have h divided by h makes 1. So what's the answer? 3. Now wait a second. Wait a second.
Whoa.
Hold on.
Yeah. The original function was just a straight line. So of course, the derivative on a line, the derivative is the same everywhere. It's always the slope. So this is yes, this was using the high-powered. Well, it's not. I don't think it's a silly problem, just because it illustrates how to actually apply this definition to find a derivative in the simplest. This is the simplest case you can do. Oh, actually, there's a simpler one, which is just f of x equals 5. Like a constant function. What's the derivative of f of x equals 5? 0. Right, so a flat horizontal line would just have a derivative of 0. And when you apply this definition, f of x plus h would be 5, and f of x would be 5. So you'd have 5 minus 5 on top, and you just, there you go, 0. Amazing, right? What did Jesse do?
Nothing. Being Jesse.
16. You know the answer to 16 before you start. That's just a test. Test your understanding. Make sure you understand the notation and how to follow that logical process. That'll just be some work for you. Okay, so I want to talk about 17. This is a more interesting one. So we'll get to get a nice result here, an interesting result. So remember that problem we talked about at the beginning of class where we said that the parabola has a derivative of a straight line?
Mm-hmm.
So here's how you would prove that that's true. How do I know for sure that's true? So you'd say this time, okay, let me divide this here. So start with a parabola function. The derivative is the limit as h approaches 0. By the way, depending on what you're looking at, you might see this h as a different symbol. It could potentially be a delta x. You might see it. You might see delta x approaches 0. Just something to keep an eye out for. Spooky, I know. Could even be a z. I don't know. Oh, and an h and delta x are the two most common ones. I prefer h. Okay, so what is my f of x plus h that I'm going to put right there? How do I write f of x plus h right there?
Just x plus h squared.
X plus h inside parentheses. So again, all I gotta do, it's very easy. I take my formula, the thing I'm taking the derivative of, and I just replace any x I see in the formula with an x plus h inside parentheses. So don't allow yourself to get confused by that. It is that simple. Okay? The tricky part, I'm just saying, getting it set up should be the simple part if you just apply that rule. Okay. Now, what's f of x? Squared. Very good. And then the bottom is just h. Very good. Okay, so there we go. We've set it up. So this reads, the derivative of this function is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so what should we do next? Ideas. Yeah, like expand this out, right? So let's actually multiply this out. So x plus h quantity squared. This is an identity we hopefully know. That is that. If you're not sure, you can go into the margin and actually multiply out x plus h times x plus h and distribute, you'll get this. But it's a good identity to just be fluent with. And then I have to subtract x squared. Okay. Do we see any cancely-wancelies available right away?
Yes.
Oh, yeah.
And then h is.
Now here let's be careful here. So let's show one more step here. So here I want to factor out an h from the top. Because this part's a little tricky. This gives people a lot of trouble. But everyone agrees with that step, right?
Yeah.
I mean, typically, when we're doing stuff like this, if you can factor something out, you almost always want to. There's usually some benefit to doing it. So I factor out that h, and now those h's divide right out. And what I'm left with here is the limit of this. And you probably see why that might confuse people. So what do I do now?
H approaches 0, it's going to be closer and closer.
So yeah, if I let my h go to 0, now, before there's a problem, right? Before I canceled it out, there was this issue of, oh, if h goes to 0, I'm divided by 0. I don't know how it'll behave in that limit. But now, well, 2x doesn't care what h is, does he? He's like, bro, 2x. Like, okay, so h can approach 0, and you just have that 2x just being what he is. So the final answer to this, it's pretty involved, right? Pretty soon this will be one of the easiest questions we ever answer, which would be, you can probably already start to imagine, what is some fast rule that gets you from this to this? Something to think about. For now, and there's no rush, we have to use this. I promise you, I'm spending as little time on this definition as possible. I'm way below average. When I took calculus, we had to use this definition to derive 100 functions. Like it got, and then it was funny when they finally revealed that actually there's all these really nice. You don't have to use the definition every time taking a derivative. It was like, oh no. So there you go. So that the long story of this proves conclusively, rigorously, that the parabola has a derivative function of just a linear function split to. So that's pretty interesting. Now, there's a little bit of notation here. Let's see what we can tell you. No, we don't have time to do that. Oh yeah, we do. We can do the cubic. So the next part of the question asks, what's f of -2 then? F prime of -2, sorry. What's the answer to this question?
-4.
-4.
Yeah.
So that is the answer to how steep is a parabola, is a basic parent function parabola, when x is -2? The answer is it's exactly -4 steepness. How about f prime of -1? -2. How about f prime 0? 0. So you can see. So taking a derivative at an actual x value is a very common thing to be asked. And it's as simple as just plugging in your x value into the derivative function. That's all you get. Easy. Okay. Okay. All right. Cubic. Before we actually do the cubic function, who knows what's going to be the annoying part of doing this? What's going to be the tricky pain in the butt part?
Oh, cubing it.
Cubing
That.
the x plus h. So there's a thing you can do. Often in math, you do this thing where you know what this part of your process that's going to be like a lot of steps, and so you do that separately. Maybe you call it a lemma. Lemma. So let's so everyone see what I'm talking about though? How doing x plus h cubed is going to be a little bit of a pain.
Yes.
Yeah.
Thank you, George.
Okay, so let's do that. Let's establish what that expression is going to be. Just wondering, does anyone know this off the top of their head? What x plus h cubed would be?
Is it like x minus h and then x?
Hold on, Jesse started first. What Jesse?
That's like are you putting it in the two thingies, or is it like just once? You know what I'm saying?
Eventually, we're going to expand it into like a standard form. It's okay. I didn't think anyone was going to know this off the top of their head. Like, Ray, do you know this off the top of your head? Sure. What do you think it is?
X cubed plus h cubed plus would be 2x cubed h plus 2x h cubed h squared. Sorry,
Very close. It's correct except with 3s instead of 2s.
Yeah. Okay.
So that's a binomial expansion. I don't expect anyone to have that memorized. It's not really. I wouldn't say it's essential to like understanding calculus or anything. So let's just encounter this. Well done, Ray. That's nice. So let's expand this. So to expand this, you'd go, okay, well, this is the same as saying x plus h times x plus h squared, right? And so that's an easy one. We've been doing that one for years. Okay, everyone's okay with that, right? Now, okay, see, it's not horrible. It's 6 terms. So x times x squared is x cubed. X times 2xh is 2x squared h. X times h squared is xh squared. H times x squared is hx squared. H times 2xh is 2xh squared. And h times h squared is h cubed. Combine like terms. This guy is friends with that guy. 1 banana, 2 banana plus 1 banana, make a 3 banana. This guy is similar to this guy. 1 banana plus 2 banana. 3 banana. And then this h cubed is by itself. So there you go. So we put that in our margin at somewhere. Just like, okay, I've established that this is equal to this. So now when I go to write my proof, I don't have to clutter up the proof with 1, 2, 3, 4 extra steps. Does that make sense? Yeah.
Mhm.
So let's do it. F prime of x then is the limit as h approaches 2. Okay, let's put f of x plus h here. Of course, you just set up the proof, right? I know we've already established that. But we're not going to jump straight to this because we need to make it a clear argument, right? So f of x plus h minus f of x over h. Is everyone okay with the setup? Great. Okie dokie. Now this is nice. We've established already that this can be written like this. So it's going to be kind of a long quotient. X cubed plus and these are very interesting, I think, if you know what you're looking for. Like Trey told us earlier what the derivative of x cubed was. You can probably see it trying to pop out. Right? See it in there?
Yeah.
Now, of course, the question is, well, how does heat pop out with nothing else? Okay, first thing.
Isn't it
Oh.
X?
Thanks, Jesse. Sorry, that last thing was not an h cubed. It's my bad. It's an x cubed. Sorry.
It's
Okay.
testing us.
Yeah, it's spice of life. Your raison, as it were. Right, Aspen? Hansely Wansley, your favorite? What can I do on top here? Let's see. We factor out h.
We just divide everything by
True. Oh, and also this other thing. You guys see the other thing? You gotta be precise. I forgot my little squared there on that second h having term.
Just having term.
So yes, it would be valid to. I think it's clear to any reader that yes, if you jump straight from this to just an expression like this, that's totally fine. It's clear enough that you've divided each term. I like to do this because a lot of students try to just cross out a single pair of h's. But anyway, guys, after those cancel out, if you plug 0 in for the h's, you see what's left over, right? X squared. So the answer to the question, the derivative of x cubed is 3x squared. Beautiful. Have a nice rest of your day.
Wait, why is it 3x plus, 3x times x equal?
Because of these terms?
Yeah.
Because now if h approaches 0,
Oh, it's all.
then these guys are going
Everything
to get
goes
shrunk to
to
0.
zippity zop.
Wow.
There you go. Hopefully you got all that.
I kept on getting the email that lady about the snack call.